In the year 1816, summer never arrived. Across North America and Europe, a strange, persistent twilight settled over the land. The sun, when visible, was a pale, dim disk in a hazy sky, casting a strange, reddish light that unnerved farmers and city dwellers alike. This was not just unusual weather. It was a global climate anomaly. In New England, snow fell in June, burying newly planted crops under a blanket of white. Killing frosts struck Virginia in July and August, a time that should have been the peak of summer's heat. Rivers in Pennsylvania were still frozen in midsummer. The seasons themselves seemed broken, a terrifying mystery that no one could explain. This chilling phenomenon became known as the year without a summer. In Europe, the situation was just as dire. Ceaseless, cold rains led to catastrophic crop failures. Famine spread across Switzerland, Germany, and Ireland, triggering food riots and mass migrations. The world was growing colder, and the cause was completely unknown. The answer to this global catastrophe lay 10,000 kilometers away and a full year in the past. On April 10, 1815, on the island of Sumbawa in modern-day Indonesia, a volcano named Mount Tambora unleashed the most powerful eruption in recorded human history. The event was an apocalyptic force of nature. This was not a typical volcanic eruption. It registered as a 7 on the Volcanic Explosivity Index, or VEI. This scale is logarithmic, meaning a VEI 7 is 10 times more powerful than a VEI 6 and 100 times more powerful than a VEI 5. The 1980 eruption of Mount St. Helens was a VEI 5. Tambora was on an entirely different plane of existence. The sheer energy it released is almost incomprehensible. It was equivalent to over 800 megatons of TNT. The sound of the explosion was heard more than 2,500 kilometers away. It was the loudest sound in recorded history. The eruption column of superheated gas, ash, and pulverized rock rocketed 43 kilometers, or 27 miles, straight up into the sky. It punched through the lower atmosphere and deep into the stratosphere. In total, the volcano ejected an estimated 160 cubic kilometers of material, enough rock to bury the entire island of Manhattan under a layer 2.5 kilometers deep. But this raises a profound scientific question. How can one volcano plunge the entire planet into a year-long winter? The most common assumption is that a simple cloud of ash blocked the sun, but that explanation is wrong. The heaviest, coarsest ash from the 1815 eruption was a regional problem. It fell out of the atmosphere within days or weeks, blanketing the surrounding islands in a thick, dark layer. While devastating locally, this ash could not account for summer snows in New England a year later. The true climate-altering culprit was invisible. The most world-altering component of Tambora's blast wasn't the rock, but the gas. Specifically, a colossal payload of sulfur dioxide. Scientists estimate the eruption injected between 60 and 100 million tons of this gas directly into the stratosphere, the stable, dry layer of our atmosphere that begins about 10 kilometers up. This destination is the critical detail. The lower atmosphere, the troposphere, is where we live and where our weather happens. Rain and wind would have scrubbed the sulfur dioxide out of the troposphere within weeks, but the stratosphere is different. It sits above the clouds, above the rain, and above the turbulent weather systems. There is very little vertical mixing between these two atmospheric layers. Once a substance is injected into the stratosphere, it stays there, for years. Tambora had just delivered a planetary-scale dose of chemicals to a place where they could not be washed away. High in the silent, frigid stratosphere, a chemical transformation began. The billions of tons of sulfur dioxide gas from Mount Tambora started to react with water vapor, the sparse moisture found at that extreme altitude. Over weeks and months, this invisible process created something new. It wasn't a cloud of dust or ash. It was a shimmering, planetary-scale veil of microscopic liquid droplets. Each droplet was a minuscule sphere of sulfuric acid. Together they formed a vast, translucent sheet of aerosols, suspended more than 10 miles above the surface. This high-altitude haze was too fine to be seen as a conventional cloud, but it was dense enough to fundamentally alter the light of the sun. An immense, silent chemical reaction had just wrapped the Earth in a reflective shroud. This brings us to the core physical mechanism of the volcanic winter. It's a concept called albedo. Albedo is simply a measure of how much solar energy a surface reflects. A dark surface, like asphalt, has a low albedo. It absorbs heat. A bright surface, like fresh snow, has a high albedo. It reflects sunlight back into space, staying cool. The sulfuric acid aerosol layer dramatically increased Earth's albedo. These tiny droplets were extraordinarily effective at scattering incoming sunlight. They acted as countless microscopic mirrors, intercepting solar radiation in the upper atmosphere and bouncing a critical percentage of it back into space. The energy never reached the ground to warm the land and oceans. The planet's energy budget was fundamentally altered. This global dimming was not caused by a shadow, but by a reflection. The sun was still shining with the same intensity, but less of its warmth could penetrate the atmospheric shield. The Earth, under its new reflective blanket, began to cool. The true, awe-inspiring power of this event was its reach. The aerosol veil didn't just linger over Indonesia. It was injected into the stratosphere, a layer of the atmosphere where weather is minimal and air flows in stable, predictable patterns. These high-altitude winds, like vast, slow-moving rivers of air, became a global distribution network. Within weeks, the veil had spread across the tropics. Within months, it had been carried poleward, reaching Europe, Asia, and North America. The chemical signature of a single volcanic eruption in the Dutch East Indies was now present in the air above the entire globe, from the Arctic to the Antarctic. One mountain had changed the chemistry of the entire sky. Its influence was inescapable, a silent testament to the interconnectedness of Earth's systems. The planet's atmosphere had circulated the cooling agent with ruthless efficiency, ensuring that no continent would be spared from the consequences. This global cooling is what directly links the atmospheric science to the catastrophes of 1816. The worldwide average temperature dropped by what seems like a small amount, just 0.4 to 0.7 degrees Celsius. But the Earth's climate system is a finely balanced engine. A small change in the global average can trigger extreme shifts in regional weather. This subtle drop in energy threw the planet's atmospheric circulation into chaos. Critical weather patterns, like the jet stream and the North Atlantic Oscillation, were disrupted. They became erratic, weak, or stuck in unusual configurations, leading not just to cold, but to bizarre and unseasonal weather events across the Northern Hemisphere. The global drop in temperature was subtle, on average, just a few degrees, but this seemingly small shift destabilized the entire atmospheric engine. It dramatically altered the path of the jet stream, the high-altitude river of air that dictates weather patterns. This disruption meant cold, Arctic air plunged south into regions where it never belonged, while monsoon seasons failed, bringing drought to Asia. The consequences for humanity were catastrophic. In North America and Europe, the altered weather led to widespread, devastating crop failures. This triggered the last great subsistence crisis of the Western world. It was a time of profound desperation. Famine gripped communities across the globe. Food riots erupted in cities as grain supplies vanished. A wave of mass migration began as families abandoned their ancestral lands in a desperate search for survival. All of this chaos was the direct echo of a single geological event on the other side of the planet. The planet, however, has a remarkable capacity for recovery. The sulfate aerosols, the tiny reflective particles that caused the cooling, could not remain in the stratosphere forever. Suspended high above the clouds, they were immune to weather for a time. But gravity is relentless. Over the course of 2 to 3 years, these aerosols slowly descended back into the lower atmosphere, the troposphere. Here, they were finally captured by water vapor, forming clouds, and washed out of the sky by rain. This gradual cleansing process explains why the climate disruptions and cold weather lingered long after the eruption itself had faded from memory. The Tambora event became a profound, if brutal, lesson for science. It stands as a stark demonstration of the deep interconnectedness of Earth's systems. A single event in the geosphere, the solid Earth, cascaded through the atmosphere, the gaseous envelope, and reshaped the biosphere, the world of living things. Today, scientists still study the 1815 eruption with intense focus. It provides a vital benchmark for refining modern climate models. By simulating Tambora's effects, we can better understand the potential impacts of future colossal eruptions, or even the proposed technologies of solar geoengineering. It reveals a fundamental truth about our world. The planet operates on a scale that dwarfs human experience. A single release of pressure from deep within the crust can rewrite the climate of the entire globe. It can alter the course of civilizations. This geological memory is not just a historical curiosity. It is a living blueprint of planetary mechanics. It shows us that the systems that sustain us are balanced on a planetary scale, vulnerable to shocks that originate miles beneath our feet. The story of the volcanic winter is a testament to Earth's immense and indifferent power. It is a reminder that we inhabit a dynamic world, where the ground beneath us is connected to the sky above us in ways we are only just beginning to fully comprehend.